The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Yesterday, we've learned about flux, and we've seen the first few examples of how to set up and compute integrals for flux of a vector field through a surface. So remember, the flux of a vector field F through a surface S is defined by taking the double integral on the surface of f dot n ds, where n is the unit normal to the surface, and ds is the area element on the surface. So, as we've seen, for various surfaces, we have various formulas telling us what the normal vector is and what the area element becomes. For example, on spheres, we typically integrate with respect to phi and theta, the latitude and longitude angles. On a horizontal plane, we would just end up integrating dx, dy, and so on. So at the end of lecture, we saw a formula, and a lot of you asked me, how did we get it? Well, we didn't get it yet, so we're going to try to explain where it comes from and why it works. Okay, so the case we want to look at is if S is the graph of a function. So, it's given by z equals some function in terms of x and y. So our surface is out here. Z is a function of x and y, and x and y will range over some domain in the xy plane, namely, well, the region that's the shadow of the surface on the xy plane. So I said that we'll have a formula for nds, which will end up being plus minus f sub x minus f sub y 1 dx dy, so that we will set up and evaluate the integral in terms of x and y, replacing every time we see z, we will replace it by f of xy, whatever the formula for f might be. So by the way, see, if we look at the very easy case where this is just a horizontal plane, so z equals constant, the function is just a constant, well, the partial derivatives become just 0, you get 0, 0, 1 dx dy. That's what you would expect for a horizontal plane just from common sense. So this is more interesting, of course, if a function is more interesting. So how do we get that? Where does this come from? So we need to figure out, for a small piece of our surface, what will be n delta s, if you want. So let's say that we take a small rectangle in here corresponding to sides delta x and delta y, and we look at the piece of surface that's above that. Well, the question we have now is, what is the area of this little piece of surface, and what is its normal vector? So observe this little piece up here. If it's small enough, it will look like a parallelogram. It might be slightly curvy, but roughly it looks like a parallelogram in space. And so we've seen how to find the area of a parallelogram in space using cross product. Right? If we can figure out what are the vectors for this side and that side, then taking their cross product will give us, and taking the magnitude of the cross product will give us the area. Moreover, the cross product also gives us the normal direction. So in fact, the cross product gives us 2 in 1. It gives us the normal direction and the area element. And that's why I said that we will have an easy formula for nds, while n and ds taken separately are more complicated, because you'd have to actually take the length or the direction of this guy. Okay, so let's carry out this program. So let's say I'm going to look at a small piece of the xz plane, the xy plane. So here I have delta x, here I have delta y, and I'm starting at some point xy. Now above that, I will have a parallelogram on my surface. I need to figure out, so this point here, the point where I start, I know what it is. It's just x, y, and, well, z is f of xy. So now what I want to find, actually, is what are these two vectors, let's call them u and v, that correspond to moving a bit in the x direction or in the y direction. And then u cross v will be, well, in terms of the magnitude of this guy, will just be the little piece of surface area, delta s. And in terms of direction, it will be normal to the surface. So it will be my, actually, I will get just delta s times my normal vector. Well, up to sign, because depending on whether I do u cross v or v cross u, I might get the normal vector in the direction I want or in the opposite direction. But we'll take care of that later, up to sign. OK, so let's find u and v. Actually, in case you have trouble with that small picture, then I have a better one here. Let's keep it just in case, in case this one gets really too cluttered. It really represents the same thing. OK? So let's try to figure out these vectors u and v. So the vector u starts at the point x, y, f of xy. And it goes to, where is its head? Well, I'll have moved x by delta x. So x plus delta x. Y doesn't change. And of course, the z coordinate has to change. It becomes f of x plus delta x and y. Now, how does f change if I change x a little bit? Well, we've seen that it's given by the partial derivative f sub x. So this is approximately equal to f of xy plus delta x times f sub x at the given point xy. I'm not going to add it because notation is already long enough. So that means my vector u is, well, approximately, because I'm using this linear approximation, delta x, 0, and f sub x times delta x. Okay. Is that okay with everyone? Good. Now, what about v? Well, v works the same way, okay? So I'm not going to do all the details. When I move from here to here, well, x doesn't change, and y changes by delta y. So x component, nothing happens. Y component changes by delta y. What about the z component? Well, f changes by f sub y times delta y. That's how f changes if I increase y by delta y. OK. So I have my two sides. Now I can take the cross product. Well, maybe I will first, factor something out. See, I can rewrite this as 1, 0, f sub x times delta x. And this one I will rewrite as 0, 1, f sub y delta y. And so now the cross product, so n hat delta s, up to sign, it's going to be u cross v. U cross v, well, so we'll have to do the cross product, and we'll have a delta x, delta y coming out. Okay, I'm just saving myself the trouble of writing a lot of delta x and delta y's, but if you prefer, you can just do directly this cross product there. Okay, so let's compute this cross product. Well, the I component is 0 minus f sub x. The y component is going to be, well, f sub y minus 0, but with a minus sign in front of everything, so negative f sub y. And the z component will be just 1 times delta x delta y. Okay? Does that make sense for? Yes. Very good. And so now when we just take, we shrink this rectangle, we shrink delta x and delta y to 0, that's how we get this formula for n ds equals negative fx, negative fy, 1 dx dy. Well, plus minus, because it's up to us to choose whether we want to take the normal vector pointing up or down. So see, if you take this convention, then the z component of n ds is positive. So that corresponds to normal vector pointing up. If you take the opposite signs, then the z component will be negative. That means your normal vector points down. Okay, so this one is with n pointing up. I mean, when I say up, of course, it's still perpendicular to the surface. If the surface has a big slope, then it's not really going to go all that much up, but more up than down. Okay. So that's how we get that formula. Any questions? No? Okay, so that's a really useful formula. So you don't really need to remember all the details of how we got it, but please remember that formula. Let's do an example, actually. So let's say I want to find the flux of the vector field z times k. So it's a vertical vector field through the portion of the paraboloid z equals x squared plus y squared that lives above the unit disk. Okay, so what does that mean? Z equals x squared plus y squared. Well, we've seen it many times. Okay, it's this paraboloid pointing up. Above the unit disk means I don't care about this infinite surface. I will actually stop when I hit a radius of 1 away from the z-axis. And so now I have my vector field, which is going to point overall up because, well, it's z times k. So the more z is positive, the more your vector field goes up. Of course, if z were negative, then it would point down, but we live above. So actually, a quick opinion poll. What do you think the flux should be? Should it be positive, 0, negative? We don't know. Okay, so I see some, I don't know, I see some negative, and I see some positive. So of course, I didn't tell you which way I'm orienting my paraboloid. So far, both answers are correct. The only one that's probably not correct is 0, because no matter which way you choose to orient it, you should get something. It's not looking like it will be 0. So let's say that I'm going to do it with a normal pointing upwards. So second chance. Okay, I see some people changing back and forth between 1 and 2. Okay, so let's draw a picture. Which one is pointing upwards? Well, let's look at the bottom point. The normal vector pointing up, here we know what it means. It's this guy. And so if you continue to follow your normal vector, see, they're actually pointing up and into the paraboloid. Okay, and I claim that the answer should be positive because the vector field is crossing our paraboloid going upwards, going from the outside, out and below, to the inside and up side. So in the direction that we're counting positively. Well, we'll see how it turns out when we do the calculation. Okay? So we have to compute the integral for flux, double integral over the surface of f dot n ds is going to be, okay, so what are we going to do? Well, f, we said, is 0, 0, z. What is nds? Well, let's use our brand new formula. So it says negative f sub x, negative f sub y, 1 dx dy. What is little f in here? It's x squared plus y squared, okay? So when we're using this formula, we need to know what's the, what little f stands for is whatever the formula is for z as a function of x and y. Okay, so we take x squared plus y squared, and we take the partial derivatives with minus signs. We get negative 2x, negative 2y, and 1 dx dy. Well, of course, here it didn't really matter because we're going to dot them with 0. So actually, even if we had even if we had made a mistake, we somehow wouldn't have had to pay the price. But still, okay. So we'll end up with double integral on S of z dx dy. Now, what do we do with that? Well, we have too many things. We need to get rid of z. So let's use z equals x squared plus y squared once more. Okay. So that becomes double integral of x squared plus y squared dx dy. And here, see, we're using the fact that we're only looking at things that are on the surface. It's not like in a triple integral, you could never do that because z, x, and y are independent. Here, they're related by the equation of the surface. Sorry if I sound like I'm, ranting, but I know from experience this is where, one of the most sticky and tricky points is, actually. That's okay. So now, how will we actually integrate that? Well, now that we have just x and y, we should figure out what's the range for x and y. Well, the range for x and y is going to be the shadow of our region. It's going to be this unit disk. Okay, so let me just do that for now. And see here, this is finally where I've left the world of surface integrals to go back to a usual double integral. And now I have to set it up. Well, I can do it this way with dx dy, but it looks like there's a smarter thing to do. Okay, I'm going to use actually polar coordinates. So in fact, I'm going to say this is double integral of r squared times r d theta. I'm on the unit disk, so r goes 0 to 1, theta goes 0 to 2 pi. And if you do the calculation, you'll find that this is going to be pi over 2. Okay? Any questions about the example? Yes? Okay, how did I get this negative 2x and negative 2y? So I want to use my formula for nds, okay? My surface is given by the graph of a function. It's the graph of a function x squared plus y squared. So I will use this formula that's up here. I will take the function x squared plus y squared, and I will take its partial derivatives. So if I take the partial of f, so of x squared plus y squared with respect to x, I get 2x. So I put negative 2x, and then same thing, negative 2y, 1 dx dy. Yes? Which k hat? Oh, you mean the vector field? Well, so it's a different part of the story, okay? So whenever you do a surface integral for flux, you have two parts of the story. One is the vector field whose flux you're taking. The other one is the surface through which you will be taking flux. So the vector field only comes as this f in the notation. And everything else, the bounds on the double integral and the nds, they all come from the surface that we are looking at. Okay, so basically, in all of this calculation, this is coming from f equals zk. Everything else comes from the information paraboloid z equals x squared plus y squared above the unit disk. Okay? So in particular, if we wanted to now find the flux of any other vector field through the same paraboloid, well, all we'll have to do is just replace this guy by whatever the new vector field is. We've learned how to set up flux integrals for this paraboloid. Not that you should remember this one by heart. I mean, there's many paraboloids in life and other surfaces too, so it's better to remember the general method. Okay, any other questions? No? Okay, let's see more ways of tackling flux integrals. But just to reassure you, at this point, we've seen the most important ones. 90% of the problems that we'll be looking at, we can do with what we've seen so far, last time and this formula. But let's look a little bit at a more general situation. Let's say that my surface is so complicated that I can't actually express z as a function of x and y. But let's say that actually I know how to parameterize it. So I have a parametric equation for my surface. That means I can express x, y, and z in terms of any two parameter variables that might be relevant for me. So if you want, this one here is the special case where you can parameterize things in terms of x and y as your two variables. So how would you do it in the fully general case? I mean, in a way that will answer your question. I think one of you, I forgot, asked yesterday, how would I do it in general? Is there a formula like mdx plus ndy? Well, that's going to be the general formula. And you'll see it's a little bit too complicated. So the really useful ones are actually the special ones. So let's say that we are given a parametric description of a surface S. So that means we can describe S by formulas saying x is some function of two parameter variables. I'm going to call them u and v. Hope you don't mind. You can call them t1 and t2. You can call them whatever you want. Okay, so one of the basic properties of a surface is because I have only two independent directions to move on, I should be able to express x, y, and z in terms of two variables. So now let's say that I know how to do that. Or maybe I should instead think of it in terms of a position vector, if that helps you. The position vector, so that's just the vector with components x, y, z, is given as a function of u and v. Okay, so it works like a parametric curve, but with two parameters. So now how will we actually set up a flux integral on such a surface? Well, because we are locating ourselves in terms of u and v, we will end up with an integral du dv. So we need to figure out how to express nds in terms of du and dv. Okay, so nds should be something du dv. How do we do that? Well, we can use the same method that we've actually used over here. Because if you think for a second, here we used, of course, a rectangle in the xy plane, and we lifted it to a parallelogram and so on. But more generally, you can think, what happens if I change u by delta u, keeping v constant, or the other way around? You will get some sort of mesh grid on your surface, and you will look at a little parallelogram that's an elementary piece of that mesh, and figure out what is its area and normal vector. Well, that will again be given by the cross product of the two sides. Okay, so let's think a little bit about what happens when I move a little bit on my surface. So, I'm taking actually a grid on my surface given by the u and v directions. And if I take a piece of that corresponding to small changes delta u and delta v, what's going to be going on here? Well, I have to deal with two vectors, one corresponding to changing u, the other one corresponding to changing v. If I change u, how does my point change? Well, that's given by the derivative of this with respect to u. Okay, so this vector here I will call, so the sides are given by let me say partial r over partial u times delta u. If you prefer, maybe I should write it as partial x, partial u, delta u, partial y. Well, it's just too boring to write. So, and so on. Okay, it means just, if I change u a little bit, keep v constant, then how x changes is given by partial x, partial u times delta u. Same thing with y, same thing with z. And I'm just using vector notation to do it this way. Okay. If you want, that's the analog of when I said delta r for line integrals along a curve. Vector delta r is the velocity vector dr dt times delta t. Okay. Now, if I look at the other side, okay, so, sorry. So let me start again. I'm running out of space. One side is partial r, partial u times delta u. And the other one would be partial r, partial v times delta v. Because that's how the position of your point changes if you just change u or v and not the other one. So now, to find the surface element together with a normal vector, I would just take the cross product between these guys. So if you prefer, that's the cross product of partial r, partial u with partial r, partial v, delta u, delta v. And so n ds is this cross product times du, dv, up to sign. I mean, also here. Depends on which choice I make for my normal vector, of course. Okay. Now, if that, of course, is a slightly confusing equation to think of. So a good exercise, if you want to really understand what's going on, try this in two good examples to look at. One good example to look at is the previous one. What is it? It's when u and v are just x and y. Okay, so the parametric equations are just x equals x, y equals y, and z is f of xy. You should end up with the same formula that we had over there. And you should see why, because see, both of them are given by a cross product. The other case you can look at, just to convince yourselves even further, so we don't need to do that because we've seen the formula before. But in the case of a sphere, we've seen the formula for n and for ds separately. So we know what n ds are in terms of d phi, d theta. Well, you could parameterize a sphere in terms of phi and theta. Namely, the formulas would be x equals a sine phi cosine theta, y equals a sine phi sine theta, z equals a cosine phi. The formulas for spherical coordinates setting rho equals a. So that's a parametric equation for the sphere. And then if you try to use this formula here, you should end up with the same things we've already seen for NDS, just with a lot more pain to actually get there because your cross product is going to be a bit complicated. Okay, but we're seeing all of these formulas, they all fit together. Somehow it's always the same question, just we have different angles of attack on this general problem. Okay, questions? No? Okay, let's look at yet another last way of finding NDS. And then I promise we'll switch to something else because I can feel that you're getting a bit overwhelmed by all these formulas for NDS. So okay, so what happens very often is we don't actually know how to parameterize our surface. Maybe we don't know how to solve for z as a function of x and y, but our surface is given by some equation. And so what that means is actually maybe what we know is not really these kinds of formulas, but maybe we know a normal vector and I'm going to call this one capital N because I don't even need it to be a unit vector. You will see. It can be a normal vector of any length you want to the surface S. So why would we ever know a normal vector? Well, for example, if our surface is a plane, say it's a slanted plane given by some equation, ax plus by plus cz equals d. Well, you know the normal vector. It's abc. Of course, you could solve for z and then go back to that case, which is why I said that one is really useful. But you can also just stay with a normal vector. Why else would you know a normal vector? Well, let's say that you know an equation that's of the form g of xyz equals 0. Well, then you know that the gradient of g is perpendicular to the level surface. Okay, so let me just give you 2 examples. If you have a plane, ax plus by plus cz equals d, then the normal vector would just be abc. If you have a surface S given by an equation, g of xyz equals 0, then you can take the normal vector to be the gradient of g. We've seen that the gradient is perpendicular to the level surface. Now, of course, we don't necessarily have to follow what's going to come, because if we could solve for z, then we might be better off doing what we did over there. But let's say that we want to do it this way. So then what can we do? Well, I'm going to give you another way to think geometrically about NDS. So okay, so let's start by thinking about a slanted plane. Okay, so let's say that my surface is just a slanted plane. So my normal vector would be maybe somewhere here. And let's say that I'm going to try, I need, of course, some handle on how to set up my integral. So maybe I'm going to express things in terms of x and y. Okay, so I have my coordinates, and I'll try to use x and y. So then I would like to relate delta s, or ds, to the area in the xy plane. So that means, I want maybe to look at the projection of this guy onto a horizontal plane. Let's squish it horizontally. So then you have here another area. Okay, so the guy on the slanted plane, let's call that delta S, and let's call this guy down here delta A. So the question, and delta A would become ultimately maybe delta X, delta Y, or something like that. The question is, how do we find the conversion rate between these two areas? See, I mean, they're not the same. Visually, I hope it's clear to you that if my plane is actually horizontal, then of course they're the same. But the more slanted it becomes, the more delta A becomes smaller than delta S, right? I mean, if you buy, if you buy land and it's on the side of a cliff, well, whether you look at it on a map or whether you look at it on the actual cliff, the area is going to be very different. I'm not sure if that's a wise thing to do if you want to build a house there, but I've been told you can get really cheap land. Okay. So anyway, okay, so delta S versus delta A depends on how slanted things are. And let's try to make that more precise by looking at the angle that our plane makes with the horizontal direction. Okay, so let's call this angle alpha, the angle that our plane makes with the horizontal direction. See, it's all coming together now. The first unit about cross products, normal vectors, and so on is actually useful now. So I claim that the surface element is related to the area in the plane by delta A equals delta S times the cosine of alpha. Why is that? Well, let's look at this small rectangle with one horizontal side and one slanted side. Well, when you project, this side doesn't change. But this side gets shortened by a factor of cosine alpha. Whatever this length was, this length here is that one times cosine alpha. So that's why the area gets shrunk by cosine alpha. In one direction, nothing happens. In the other direction, you squish by cosine alpha. So what that means is that, well, okay, so we'll have to deal with this. And of course, the one we'll care about actually is delta S expressed in terms of delta A. But what are we going to do with this cosine? It's not very convenient to have a cosine left in here. So remember, the angle between two planes, it's the same thing as the angle between their normal vectors. So if you want to see this angle alpha elsewhere, what you can do is you can just take the vertical direction. Let's take k. Then here we have our angle alpha again. Well, so in particular, cosine of alpha, I can get, well, we know how to find the angle between two vectors. Right, so if we have our normal vector n, we'll do n dot k, and we'll divide by length n, length k. Well, length k is 1. That's one easy guy. Okay, so that's how we find the angle. So now I'm going to say, well, delta S is going to be 1 over cosine alpha delta A, and I can rewrite that as length of n divided by n dot k times delta A. Now let's multiply that by the unit normal vector, because what we care about is not so much ds, but actually n ds. So n delta S will be, I'm just going to multiply by n, well, let's think for a second. What happens if I take the unit normal n and I multiply it by the length of my other normal big N? Well, I get big N again, right? This is a normal vector of the same length as n. Well, up to sign, but yeah, actually maybe I should. The only thing I don't know is whether this guy will be going in the same direction as big N or in the opposite direction. Right? Say that, for example, my capital N has length, I don't know, length 3, for example. Then the unit normal vector might be this guy, in which case, indeed, 3 times little n will be big N. Or it might be this one, in which case 3 times little n will be negative big N. But up to sign, it's n. And then I will have n over n dot k delta A. And so the final formula, the one that actually we care about, in case you don't really like my explanations of how we get there, is that nds is plus or minus n over n dot k dx dy. Okay, that one is actually kind of useful, so let's box it. Now, just in case you're wondering, of course, if you didn't want to project to xy, you would have maybe preferred to project to, say, the plane of a blackboard, yz. Well, you can do the same thing, okay? To express nds in terms of dy dz, you do the same argument. And simply the only thing that changes is instead of using the vertical vector k, you use the normal vector I. So you would be doing n over n dot I dy dz. and same thing. Okay, so just keep an open mind that this also works with other variables. But anyway, so that's how you can basically project the vector surface area element onto the xy plane in a way. Okay. So let's look at the special case just to see how this fits with stuff we've seen before. Let's do a special example where our surface is given by the equation z minus f of xy equals 0. Okay, that's a strange way to write the equation z equals f of xy that we saw before. But now, it looks like, well, some function of xyz equals 0. So let's try to use this new method. Okay. So let's call this guy g of xyz. Well, so now let's look at the normal vector. The normal vector would be the gradient of g, we said. What's the gradient of this function? So gradient of g, well, partial g, partial x, that's just negative partial f, partial x. Gradient g, sorry, the y component, partial g, partial y, is going to be negative f sub y, and g sub z is just 1. So now, if you take n over n dot k dx dy, well, it looks like that's going to be negative f sub x, negative f sub y, 1, divided by, well, what's n dot k? If you do that with k, you'll get just 1. So I'm not going to write it, dx dy. See, that's, again, our favorite formula. So this one is actually more general because you don't need to solve for z, but if you can solve for z, then it's the same as before. Okay. I think that's enough formulas for NDS. So after spending a lot of time telling you how to compute surface integrals, now I'm going to try to tell you how to avoid computing them. And that is called the divergence theorem. And we'll see the proof and everything and applications on Tuesday, but I want to at least state the theorem and see how it works in one example. It's also known as the Gauss-Green theorem or just the Gauss theorem, depending on who you talk to. So the green here is the same green as in Green's theorem, okay? Because somehow that's a space version of Green's theorem. So what does it say? It says, so let's say it's a 3D analog of Green for flux. What it says is if S is a closed surface, okay, so remember it's the same as with Green's theorem, we need to have something that's completely enclosed. So you have a surface, and there's somehow no gaps in it. There's no boundary to it. It's really completely enclosing a region in space that I will call D. And I need to choose my orientation. So the orientation that will work for this theorem is choosing the normal vector to point outwards. Okay, so n needs to be outwards. Okay, so that's one part of the puzzle. The other part is a vector field. I need to have a vector field that's defined and differentiable everywhere in D. so same restrictions as usual, then I don't have actually to compute the flux integral. Double integral of f dot n ds over the closed surface S. So I'm going to put a circle just to remind you it's got to be a closed surface. Okay, that's just notation to remind us, closed surface. I can replace that by the triple integral over the region inside of divergence of f dv. Now I need to tell you what's the divergence of a 3D vector field. Well, you'll see it's not much harder than in the 2D case. What you do is just so say that your vector field has components P, Q, and R, then you will take P sub x plus Q sub y plus R sub z. Okay, so that's the definition. It's pretty easy to remember. You take the x component, partial respect to x, plus partial respect to y of the y component, plus partial respect to z of the z component. Okay? So, for example, last time we saw that the flux of the vector field zk through a sphere of radius a was 4/3 pi a cubed by computing the surface integral. Well, if we do it more efficiently now by Green's theorem, so we're going to use Green's theorem for this sphere. Because we're doing the whole sphere, it's fine, it's a closed surface. We couldn't do it for, say, a hemisphere or something like that. We need to, well, I mean, for the hemisphere, we'd need to add maybe the flat face at the bottom or something like that. So Green's theorem says that our flux integral can be actually replaced by the triple integral over the solid ball of radius a of the divergence of zk dv. But now, what's the divergence of this field? Well, so you have 0, 0, z, so you get 0 plus 1. Looks like it will be 1. So if you do the triple integral of 1 dv, you will get just the volume of the region inside, which is 4/3 pi a cubed. And so it was no accident. In fact, before that, we looked at also xi plus yj plus zk, and we found 3 times the volume. That's because the divergence of that field was actually 3. So very quickly, let me just say what this means physically. Physically, see, this guy on the left is the total amount of stuff that goes out of the region per unit time. So I want to figure out how much stuff comes out of there. What does the divergence mean? The divergence means, well, it measures how much the flow is expanding things. It measures how much, I said probably when we understood 2D divergence, it measures the amount of sources or sinks that you have inside your fluid. So, you know, now it becomes common sense. If you take a region of space, the total amount of water that flows out of it is the total amount of sources that you have in there minus the sinks. Okay? I mean, in spite of this common sense explanation, I mean, we're going to see actually how to prove this, and we'll see how it works and what it says.